playing with the standard inflationary paradigm. And in this paradigm, what happens is that you have this nearly homogeneous and isotropic soup of stuff in the early universe. And there are some random fluctuations, but they're very, very tiny random fluctuations. So something like this, if you like. And over time, these fluctuations, which are defined as density perturbations divided by the mean density, okay, over time, these fluctuations will grow via gravitational instability. Okay, so in other words, those regions that are already dense will get even denser, and those regions that are empty will get even emptier. And those dense regions will eventually collapse to form the structures like galaxies and galaxy clusters and whatever that we see today. So this is from snapshots from a simulation where you start from homogeneous matter density field, and then eventually end up with a galaxy cluster here. Now, so roughly speaking, this is a schematic of illustrating what's happening. So here is a spatial coordinate x, and this here shows you the fluctuations around of the density field around some mean value. And here you have, well, the mean value is 0, actually. The fluctuation has to be 0 overall, of course. And so you have, it's just fluctuations. Now, over time, these fluctuations will grow, okay? So this dense region here will become even denser, and here is an empty region with a slightly negative fluctuation, and this region will become even emptier, okay? So these dense regions here are the regions where you expect galaxies and halos and whatever to form, and these empty regions here that become even emptier are what we call the voids. Now, so how does the whole neutrino thing come into play? Okay, so as we have discussed many times, we have this cosmic neutrino background, and if neutrinos have masses, then we expect this background to also be a kind of dark matter. Okay, so the temperature of these neutrinos today is 10 to the minus 4 electron volt or 2 Kelvin. We have a lot of these things around, about 100 per cubic centimeter per family of neutrinos and antineutrinos. As I've also shown you the total non-relativistic energy density expressed in terms of this reduced energy density parameter and how this relates to the neutrino mass sum. Now, as we all know, observational evidence tells us that we have dark matter, and this comes in as at a reduced energy density parameter of 0.25. So the immediate question you can ask is, can standard model neutrinos be the dark matter? And the answer is, as you probably already know, it's not. It cannot be a dark matter. It cannot be a dark matter. Well, there's one obvious reason. The one obvious reason is that if you try to figure out what kind of masses you need to get to 0.25 electron volt, this number is something like, I think 3 or something like that. Yes, for each neutrino, assuming they're degenerate. And we already know that neutrinos are not that massive, okay? But there's a deeper reason. And this has to do with what we call free streaming, okay? So look at this picture here again, where you have this primordial density fluctuation. Let's suppose that the neutrinos make up all the dark matter, okay? And let's suppose you have this density fluctuation here in neutrino dark matter. Now, we expect, if structures were to form, then we should see the structure, grow, the fluctuation grow into this red line over here. And to determine whether structures can form from this lump of stuff, there are two critical quantities that we need to consider. The first is called the instantaneous collapse timescale, and that basically tells us the timescale that is required for this lump of stuff to collapse to 0. Okay, and we also have to worry about a quantity called the instantaneous escape timescale. And we need to worry about this because the neutrinos move quite fast. Yeah, even though they were created relativistic, and even though they have gone through a lot of redshifting, they still come with a non-trivial velocity. Okay, so that allows them to escape from this gravitation, from this lump to infinity. Okay, so these are the two timescales that we need to consider. And once we have these two timescales in play, then we naturally classify the behavior of this neutrino perturbation into two regimes. Okay, one is the regime of growth, and this happens when the collapse happens faster than the escape of the neutrinos. Okay, so in other words, if you look at the collapse time scale, it's so short that the lump manages to collapse before the neutrinos manage to escape. Okay, so collapse time scale is much shorter than the escape time scale. And in that case, this fluctuation here will grow from the green line to the red line. But you also have the other limit, okay? And that's the erasure limit. And the erasure limit is exactly the opposite. The collapse doesn't happen fast enough. you don't have enough gravitational pull, and the neutrinos manage to fly away, okay? And in that case, what would happen is that instead of having this perturbation grow to become bigger and bigger, it actually becomes erased, okay? And that is really the central reason why it is that neutrinos cannot be the dark matter, because if I now put in real numbers, then what I would find is the following. It looks like I have somehow deleted one slide, a critical slide. I'm really sorry about that, but this is the free streaming, what we call the free streaming time length scale. And we established this free streaming length scale by equating the collapse time scale with the escape time scale. And so, in other words, all you have to do is to take the velocity of the neutrinos, multiply by the collapse time scale. And the velocity of the neutrinos we can establish, and unfortunately, I don't know why I managed to delete that slide, but it's something that is about 100 kilometers per second for today for 1 electron volt neutrino, okay? Anyway, if you plug that in, if I had an expression, I plug that in, then I end up getting this expression for this instantaneous free streaming time scale. Okay, so it's 1.2. This is the matter density today. Set here as the redshift parameter. Mu here is the neutrino mass. And so what this means is that unless the density fluctuations are somehow regenerated by other means, then at any time, at any redshift, the relic neutrino cannot form structures on length scales that are less than the free streaming time scale. And now that's an instantaneous time scale. And of course, this scale here is dependent on the redshift. But we can also figure out what is the maximum instantaneous free streaming length scale that is relevant for structure formation. And that length scale is attained at the time when the neutrinos just become non-relativistic. Okay, and we can establish when the neutrinos go non-relativistic. It's basically just given by the mass of the neutrinos divided by 3 times its temperature. And then we use this relation, plug it into the previous expression, we end up with this expression here. Okay, so you have, well, again, the matter density dependence on the neutrino mass. And if you plug in, say, a 10 electron volt neutrino, what you'll find is that this maximum instantaneous free streaming scale is about 45 megaparsec. Now, galaxy has an extent of about 10 kiloparsec. A galaxy cluster about 1 megaparsec, okay? And if my free streaming scale maximum free streaming scale is 45 megaparsec, then I'm gonna have a lot of trouble forming galaxies and galaxy clusters, because on these scales, the neutrinos would prefer to fly away, okay? They don't like to clump. So that's the reason why it is that neutrinos are such a bad dark matter candidate. And I showed you this simulation before, I'll show it again, why not? So there are 2 cosmologies here. One has cold dark matter, and the second one here is actually mostly neutrinos and then a little bit of cold dark matter. The neutrinos here add up to 6.9 electron volt in masses. And you can see immediately that the effect of free streaming. Okay, so you have a lot of empty regions here because the neutrinos are just flying out. They don't like to clump. Okay, this one here is cold, entirely cold dark matter, and so you can form tiny structures. And then this is what tells us that the dark matter that we are seeing today has to be cold. Good. So then the next question is, if the neutrinos are so useless, they're not dark matter, why are we bothering with them anyway? Well, we bother with them because we know the neutrinos are massive, okay? We know that from neutrino oscillations that at least one neutrino mass eigenstate has a mass that is 0.05 electron volt, okay? And furthermore, we have an upper limit on the effective new E mass, and that's about 0.9 from the Catherine experiment. So what this allows us to deduce immediately is a range for the reduced energy density for the neutrinos that we expect to see today, and that ranges between 0.1% to 6%. Okay? So what this means is that even though the neutrinos are not, the relic neutrinos cannot be a kind of dark matter, cannot be the dark matter, it can nonetheless form a subdominant component of the total dark matter content in the universe, okay? And furthermore, because these neutrinos are free streaming as opposed to being cold, they leave a rather interesting signature in the large scale structure, okay? Simply by virtue of them being able to free stream away. And what it means in turn is that we can use this free streaming imprint to try to establish what is omega nu in the present time. and from there to put a constraint on the neutrino mass. In other words, to narrow this range even further. Okay, so just to drive that point home, we're not trying to explain dark matter with neutrinos, we're just considering neutrinos there as a subdominant component of the total dark matter content. So so what are we looking for? Well, essentially what we're looking for is the fact that, yes, you have neutrino free streaming, and as I explained 2 slides ago, if neutrinos form all of the dark matter, you will have trouble making structures. But now we're looking at a mixed cold dark matter and neutrino dark matter cosmology. So what happens is that you have another source that is able to cluster, and that's the CDM. The cold dark matter is able to cluster efficiently. And so instead of having all the density fluctuations being erased on scales beneath the free streaming scale, we don't have complete erasure anymore. We just have a slight suppression, okay? Because the neutrinos are just a little bit bad at clustering because they have so much kinetic energy. Okay, so so that's basically what we're looking for when we try to determine a neutrino mass from cosmological observations. So here's a bit of a schematic to illustrate what's happening. I show this all the time. And so here is a potential well, which has a spatial extent of lambda, and I don't know what I did with my slides. Again, looks like I've deleted things I shouldn't have deleted. But anyway, so this is a big potential well with a spatial extent that is larger than the free streaming scale. So this potential well here is able to capture dark matter, cold dark matter, and massive neutrinos, so that's fine, okay? And on the other hand, on length scales that are smaller than the free streaming scale, this is a small potential well, so it's only able to capture the cold dark matter, and it's not able to capture the neutrinos. So that's what we're looking at. Here's actually a simulation illustrating that, what I described just now. So here, on the left-hand side, we have this is a mixed dark matter simulation, and on the left-hand side, it shows the cold dark matter component, and you see all these little fine structures. But if you now go to the right and look at this picture over here, this is the neutrino component. So they look kind of similar. You have a big lump of stuff here, a big lump of stuff there, but this one is all smeared out, okay? And that's because the neutrinos don't like to fall into the small potential wells. And if you look at the neutrino momentum, and look at how they cluster one by one, and this is like this lowest momentum to the highest momentum, you see this feature again, okay? So this is the lowest momentum neutrinos. This picture here looks still kind of like this one, but I mean, not completely like this one, because they're still free streaming, but a lot more like this one than this one, because it's clustering a bit. But as you crank up the neutrino momentum, the harder it is for them to fall into potential wells, okay? Sorry? So you will see a little bit less small scale structures, but you won't be able to see it by eye. Yeah, because 0.05 electron volt is a tiny effect, as a percent level effect. On this picture, you won't be able to see it. But that's why we have to go to summary statistics to the power spectrum to look at that effect. But looking at it from a snapshot is impossible. It's just a percent level effect. But anyway, so that's this non-clustering as I was talking about in the first picture. Now, an even more interesting thing happens if you wait a little bit of time for this, this process of capturing neutrinos and cold dark matter on the left-hand side and capturing only cold dark matter and not neutrinos on the right-hand side. Because if you wait a little bit of time, what would happen is, and you look at these two potential wells again, what would happen is that you find that the one on the left has captured all of these neutrinos and cold dark matter, and as a result, the potential in the sense of the metric perturbations in my line element in my conformal Newtonian gauge, okay? These potential will stay the same depth. At least that is exactly true during matter domination. Did I say radiation domination? No, matter domination. I don't know what I did with these slides, sorry. Then on the other hand, if I look at the potential well on the right-hand side, this is a small potential well that is only able to capture the cold dark matter. And it's not capturing all the neutrinos. So what happens here on this side is that you have a mismatch between the total matter density that is there in the universe and the amount of this total matter density that is actually able to cluster, okay? And this mismatch causes the potential to decay away. And when we try to measure neutrino mass from cosmology, what we're really doing is to look for this kind of scale-dependent gravitational potential decay. Okay, so here's another schematic showing what is happening. So this here is basically a plot of the perturbation wave number. So basically, if lambda is the size of the potential well, this k here is just the 2 pi divided by lambda, because cosmologists like to talk wave numbers. We like to work in Fourier space. And these two lines here are basically like the depth of the potential wells, if you like, or you can call it a perturbation spectrum. And on the large scales, you're going, on the left are the large scales, on the right are the small scales. And we have two cosmologies, one that is cold dark matter only, that's the blue one, and the red one is the one that is a mixed cold neutrino dark matter universe. And these two cosmologies start off with potentials that are exactly the same on all scales, but if you wait a little bit of time, because of neutrino free streaming, you will always end up getting this kind of step-like feature, okay, because of the non-clustering neutrinos. And this roughly where this step begins corresponds to the wave number at the time when the neutrinos become non-relativistic. Okay, so that's the signature that we expect to see. That's a schematic. This is the real thing. And so this is computed from linear perturbation theory, and the green here corresponds to the case of zero neutrino masses. The blue corresponds to what happens if you replace some of the cold dark matter with massive neutrinos, but keeping the total matter density the same. Okay, so same total matter density, but in one case you have some stuff that does not like the cluster. And you can see immediately this suppression in the power spectrum. Okay, so this is a summary statistics I was saying, where you can see the suppression. That is impossible to see by eye in a snapshot. And the suppression goes like the neutrino fraction, which is itself dependent on the neutrino mass. Another thing to note is that the larger the mass sum of the neutrinos, the stronger the suppression that you would expect. That's the basic signature. Okay, there is some dependence on exactly how you arrange the masses. So what mass ordering actually that you have exactly, in fact, matters to the amount of suppression that you get here, as well as the transition region over here. But this is a dominant signature, just the mass sum. This one here, I don't know what this is. I don't know where I got this picture from, and I don't remember what they assume. But it's said that's the dominant signature. You get some small corrections if you deviate from degenerate or normal or whatever. Yeah. Well, the thing is that because the differences between the different mass orderings only really appear in a transition region, and to an extent over here, it's at the moment not possible to tell. In the near future, also not possible. Okay, so that's the matter power spectrum, and there are a large number of probes that are able to measure this matter power spectrum in different parts of the K-space. And so you have the CMB primary anisotropies that's essentially probing the matter power spectrum at a high redshift of 1,000. There's also CMB lensing, which is basically we look at how the paths from the photon paths from the CMB are bent by the intervening large-scale structure, and that is most sensitive to the large-scale structure at a redshift of 3 to 4. Galaxy clustering surveys, or BAO, are essentially catalogs of galaxy angular positions and redshift, and then you look at how the clustering statistics of these galaxies. Cosmic shear is another word for weak gravitational lensing, so you're looking at distant galaxy images and how they are distorted. Okay, and that is redshift of 1 to 2 or so. Cluster abundance is basically just counting clusters and then binning them by mass. And Lyman alpha are the fluctuations that we should expect to see in the intergalactic hydrogen clouds, and they are mainly sitting around at 2 to 4, ratio of 2 to 4. Okay, so now it's important to realize that we need combinations of these probes to really determine a neutrino mass. In particular, we need to have some sort of anchor on the large scales, and that is because if I only measure the lower part, there are a lot of degeneracies. Okay, so I need to anchor this large scale part here at small values of k, and that's basically the role of the CMB anisotropies. They are there; those measurements are there to anchor down the basic cosmology, like lambda CDM, for example, anchoring down these parameters like the matter density, the baryon density, the spectral index from inflation, the primordial fluctuation amplitude from inflation. Tau is a astrophysical parameter called the optical depth, and h is the Hubble expansion rate. And then once you have that, you can start adding these additional probes to give you more handle on this part of the power spectrum. Okay. Right, now, one more thing I want to highlight is that when I show you these two lines here, I mentioned that they have been computed using linear perturbation theory. And that was also what I talked about earlier in the first lecture today, that we take GR and take Boltzmann equation, linearize everything, because that works very well on large scales. But as with all perturbation theories, they break down at some point. And in the case of cosmological perturbation theory, they break down at late times and on small scales. And if I ask, when does linear perturbation theory break down today at z equals 0? Or actually more accurately, when is linear perturbation theory valid in the sense that it is able to correctly predict the observables to 1%, okay? Then it's here. This line indicates the region of validity. So it's valid, perturbation theory is valid on this side, okay? And if you push linear perturbation theory to beyond this line to these values of k, then technically they are not percent level accurate. The theory is not percent level accurate anymore. But this is a redshift dependent statement, because if I go back to look at observables at a higher redshift, then things would have been less nonlinear at an earlier time. And in fact, if I ask the same questions, pose the same questions, but demand percent level accuracy at set of 1, then the line shifts a little bit to the higher value of k. And if I demand percent level accuracy at z equals 3, it shifts to a higher value of k again. Okay? So if I now look at this rather messy plot and all the vertical lines, and then ask which probes are linear and which probes are nonlinear, then what you will the conclusion you'll come to is that the CMB anisotropies are very linear probes, so you can calculate everything using linear perturbation theory. The lensing potentials are also pretty well under control from a linear theory perspective, because the redshift is 3 to 4. Galaxy clustering surveys are, well, typically out to a redshift of 1, so it's already sort of encroaching into the nonlinear region. Cosmic shear is pretty nonlinear, cluster abundance is nonlinear, and Lyman alpha is definitely a very nonlinear. Okay? But even this picture doesn't tell you the whole story. It doesn't tell you the whole story because there are nonlinearities and nonlinearities, and not all nonlinearities are equal. And some are actually rather easy to compute. Okay? So what I have here are the different types of probes that we have: CMB, BAO, cosmic shear, etc. And then I've classified them, well, in my own classification of types of nonlinearities that they suffer. So all the probes here, with the exception of CMB, suffers from some degree of nonlinear clustering that develops in the dark matter. And this is called a collisionless kind of clustering. But then there are also probes that suffer from baryonic astrophysics, in the sense that the observable itself, when you try to predict it, you need to put in baryonic astrophysics as an input in your calculation. So in particular, we're talking about here, the Lyman alpha, which is a hydrogen distribution. And when you simulate the hydrogen distribution, you need to know your star formation rate, you need to know your supernova feedback, etc. Everything has to go into your simulation before you can predict how the hydrogen clouds are distributed. Yet another form of nonlinearities that comes in, which is totally unpredictable, and can only be, you can only kind of guess, is what I call empirical tracers or proxies. And two types of probes are particularly prone to this. The first is the galaxy power spectrum. And essentially what's happening here when you use galaxies to infer the matter power spectrum is that you're making the assumption that the galaxy clustering traces the underlying dark matter density, which sounds like a good idea, but it's not completely good, because at some scales, this proportionality would break down. Okay, now people try to model it nonetheless, but there is the galaxies are a tracer of the dark matter, and assuming that they trace each other exactly is an assumption. Okay. Another one is cluster abundance, where you basically bin the clusters that you observe by the masses, but clearly we can't really measure the mass of a cluster, and we have no way to measure it, okay, except through maybe lensing. If you have strong lensing, you can probably deduce the mass of a cluster, which can be done. But most of the cluster measurements that we see here use, for example, the X-ray temperature of the cluster as a proxy for the mass. And the idea is that the more massive the cluster is, the higher the X-ray temperature. Again, that sounds like a very good idea, but the relation is not necessarily one that you can predict exactly, and there's a lot of scatter around it. So we need to be mindful that some of these nonlinearities are inherently difficult to model. Okay, just a very brief word about those nonlinearities that are fairly easily calculable. So those are the ones that are occurring in the clustering of the collisionless dark matter. So dark matter is, well, non-interacting stuff. Okay, so the only thing they do is to move under each other's gravity, and that's it. Okay, so they are called collisionless. These kind of nonlinearities that develop in the dark matter are called collisionless nonlinearities, and they are really just nonlinearities arising from gravitational interactions. Same with neutrinos, of course. And what this plot shows here is, again, the suppression. It's a matter-power spectrum ratio of a neutrino mass, a cosmology with a large neutrino mass versus a cosmology with a small neutrino mass. So you see this suppression in the power spectrum. And the purple line here is the result that you get from linear perturbation theory. And if you try to push linear perturbation theory to high order, what you see immediately is that you get a stronger suppression. But even this calculation is not completely right, because things go too nonlinear, and you need to use a non-perturbative method. And in that case, in cosmology, your non-perturbative method is essentially an n-body simulation. And these dots here shows the actual prediction of the suppression that we should expect to see in the matter-power spectrum once we get into the nonlinear regime. Okay, this is just a schematic of an n-body simulation. And so essentially what you do is that you have a simulation box. It's a standard, by the way, it's a standard thing that we use to calculate nonlinear CDM evolution. What you do is that you put a box there, impose periodic boundary conditions, because if you're in the universe, we have homogeneity and isotropy on large scales, so you should basically have the block repeated many, many times infinitely. So that's the periodic boundary conditions. We discretize the cold dark matter fluid into particles. We use 10 million to 10 billion of these particles, depending on what you're trying to do. And then you just evolve each block of particle according to these fairly simple equations of motion, okay? And there's a Poisson equation that you need to solve at every time step, depending on what fluctuations you have the gravitational potentials, and then having figured that out, you feed that back into your equation of motion, and you keep the particles moving, okay? So it is really quite simple, the idea. But of course, the implementation and making this sort of simulation run fast is an art, science in itself, whatever, the art maybe. Anyway, so it's a very active field of research. This is the picture for cold dark matter. You can, of course, also do exactly the same thing with neutrinos. But what makes it kind of hard, what makes these simulations rather nasty for neutrinos is that the neutrinos are dispersive. They're flying in all directions, and they're very fast. So this means two things. The first is that instead of having, putting one particle, CDM particle on each, everywhere, you need to have basically a collection of neutrino particles per CDM particle to model the fact that you have a dispersive gas, okay? So for every blue particle, you have a number of neutrino particles to model this free streaming effect. And the second thing is that these neutrinos are extremely fast, yeah? So you have to initialize them with an extremely large initial velocity, and they fly around very quickly across the box. So in order to track them properly, you need very small time steps. So overall, what it means is that doing this sort of simulations is, well, noisy, unless you have a huge computer, and takes a very long time, unless you have a huge computer. So finding ways to make these simulations more efficient, simpler, and more accurate is actually an active area of research. And unfortunately, I don't really have time to talk in detail, but it's something that I like to do these days. Okay, but anyway, a couple of words on a neutrino mass bound, since I guess that's what people care about the most. Well, there's no cosmological neutrino measurement yet, but we do have some constraints on the neutrino mass sum, and they typically fall in the range 0.1 to 0.3 electron volt, depending on exactly how you do the analysis. And So this is a table that I took out of this paper. It's several years old, but it still illustrates the point very well, where the first line here corresponds to the most basic fit you can do. So you just have your baseline lambda CDM, you add to it the neutrino mass sum, so you have 7 fit parameters that you vary in your MC fit. And then there are 3 columns correspond to exactly how you model the neutrino spectrum, the 3 neutrino masses. This is the easiest degenerate mass because you only have 1 mass parameter in that game. And then you can have the normal hierarchy, which will be 3 mass parameters, and the inverted hierarchy, also 3 mass parameters that you have to vary at the same time. So these 2 are really horrible to do. I've been informed by the authors of this paper that they take forever. Anyway, so you get these numbers, and already you see that the mass bound depends on what mass ordering you assume, okay? Not by a lot, but still there's a dependence. Then if you go down to the second column and the third column and so forth, so on and so forth, and what we're doing here, what they did here is basically to add 1 extra free parameter. In the second column here, they added what's called a primordial tensor modes, tensor to scalar ratio. This is motivated by inflation, because inflation is supposed, in some inflation models, you get primordial gravitational waves, and this R parameter is basically a quantification of how large the gravitational wave and background amplitude is. Okay, and again, you see that you get slightly different numbers. In these next 3 rows here, you have various ways of introducing a dynamical dark energy. So in the first case, it's basically allowing this equational state parameter of dark energy to deviate from -1. Again, you get some different numbers. Actually, you get a relaxation of the neutrino mass bound. Over here, this is another kind of dynamical dark energy, and you get a relaxation again. And this case is also dynamical dark energy, but they were restricting the equational state to be larger than -1. In other words, they don't want the dark energy to go phantom. And what you see here is that the neutrino mass bounds actually become quite a bit worse. Okay, so that's the moral of the story of this table here is that there's no one number that people quote, because it really depends a lot on how exactly you do your analysis when you derive these neutrino mass bounds. There's a factor of 3 variation just in this within this table over here. So I normally would just say 0.1 to 0.3. It depends on how you do it. Okay. Okay. Now, last thing is that these are kind of standard variations that a lot of people do. You can be very adventurous and start playing around with the physics of the neutrinos themselves and the properties of the neutrino background in order to get away from these rather tight bounds. And some of the scenarios people have considered include neutrino decay, spectral distortion, and late-time neutrino mass generation. These games, when you play them, will buy you a fair bit more room than the games on the previous slide. But you will have to accept these scenarios, these non-standard physics scenarios. So let me just go through them very briefly. This is the case of non-relativistic neutrino decay from these people a couple of years ago. And essentially they were saying that if you have the neutrinos decaying with a lifetime of 0.1 million years, then it is possible to relax the neutrino mass bound by maybe a factor of 3, okay? Not a lot, but still it can be done. This one here considers something rather fun, I don't know. And essentially what they were trying to do is to engineer distortion to the Fermi-Dirac distribution. So normally in the standard case, the neutrinos come with a Fermi-Dirac distribution. But suppose you have some funny process that makes the Fermi-Dirac distribution deviate, okay, from itself. Okay. Then it turns out that with these spectral distortion, this spectral distortion effect, you can again relax the neutrino mass bound by a factor of 2 or so. This is actually an older paper, so they were fitting Planck 2015 paper. So what you should be comparing is 0.18, which is a standard FD case, and then with spectral distortion, you get a factor of 2 distortion. Relaxation. Okay, that's kind of tame. These guys here, they decided to be adventurous, and they thought, well, what if the momentum distribution is actually a Gaussian? Now, I don't know what can give you a Gaussian momentum distribution, but they did it anyway, these people. And what they found is that you can even relax the neutrino mass bound to 3 electron volt. Okay, but these scenarios are probably a bit out there, but it does illustrate that there are assumptions that there are assumptions going into these bounds. A lot of them are reasonable, but you can question them. Last but not least, scenario of Varley and Funke, where they decided that it would be fun to generate a neutrino mass through some late time phase transition when at a temperature of merely electron volt, so very low redshift. And what they found phenomenologically is that if you have such a phase transition only after a set of 1, then so neutrino is massless throughout the evolution history of the universe, and they only become massive at a very low redshift, then a mass bound as large as 1.46 is okay. So anyway, so that's all I have to say about the neutrino mass sum and their constraints. And does anyone have anything to ask me very quickly? I'll take that as a no, and I'll move on. Okay, something different. So I'm going to talk about now in this next 25 minutes or so about relativistic neutrinos and their free streaming effects and non-standard interactions. So we remember this picture, right, from yesterday, I guess, about formation of the cosmic neutrino background. And the idea, what this schematic here illustrates, is that at high temperatures, you have the neutrinos scattering off electrons and positrons and other neutrinos, and they're all kept in a kind of thermal equilibrium. And then afterwards, at temperatures of below 1 MeV, you have neutrino decoupling, and after that time, the neutrinos are all going in a straight line and free streaming to infinity. Now, free streaming sounds like a terribly boring thing, but actually, it's not boring. And that is because if you're free streaming in an inhomogeneous and anisotropic background, then what the free streaming can do is to develop anisotropic stress. Okay? So pressure you'll get anyways, just because things are dispersing, you'll get pressure. But if in addition your background is inhomogeneous and anisotropic, you can also get anisotropic stress. I'll say more about that in the next slide. But just to go back to this team you knew over here, the anisotropic stresses are essentially these diagonal terms here in the space-based part of the stress energy tensor. Now, fundamentally, there's nothing different about relativistic particle free streaming and non-relativistic particle free streaming. But the difference is that if you have non-relativistic particle free streaming, these anisotropic stress or pressure perturbations will be tiny. So we don't care about them. You only care about their effects on the energy density. But if things are relativistic, then pressure and anisotropic stress come into play. Okay, so that's the difference. Okay, so why is it that, so I said that in homogeneous and anisotropic background, the neutrino free streaming is interesting because they generate anisotropic stress. What does that mean? Well, or momentum anisotropy, that's another word for it. Well, you can understand that by just looking at this schematic over here. So what I have in the yellow and white, this is basically a series of sinusoidal potential wells, okay, just like that. And now you imagine that I have some neutrino fluid that is sitting at the top of the potential well. Now, think about first those neutrinos that are horizontal, okay, horizontal in this slide, okay. And what you have is that these neutrinos are not encountering any potential variation whatsoever. They're just going in the essentially flat space as far as their trajectory is concerned, okay. So they don't see anything. They're just moving. Right? On the other hand, if you think about those neutrinos that are going down or going up, what they see is, well, when they start moving, they'll fall into a potential well, and they'll climb up, and they'll fall into a potential well, and so on and so forth. So if I just look at this particular element here, what I can immediately conclude is that those neutrinos that are just about to fall into a potential well would be a little bit hotter, because when they're falling in, they pick up some kinetic energy. So that's what is meant by in homogeneous background inducing an anisotropic stress. Now, why is this interesting? This is interesting because now I go back to the line element in the conformal Newtonian gauge. Okay, I have two perturbations here, psi and phi. I told you earlier that these are kind of like gravitational potentials, but actually they're not exactly gravitational potentials, and in fact they can be different. And if you work through the Einstein equation, what you'll find is that the difference between phi and psi is actually proportional to this quantity sigma, and that is the anisotropic stress in the universe. Okay, so mainly in CDM, the anisotropic stress comes from photons that are free streaming after photon decoupling, and it comes from ultra-relativistic neutrinos that are also free streaming. So this difference between phi and psi are proportional to sigma. And this is interesting because if you are changing phi minus psi around CMB times, then the CMB perturbations themselves will feel the changes, okay? And this is observable in the CMB TT power spectrum. And here's a picture from a while ago, from 20 years ago now, almost 20 years ago, of what happens if you have standard neutrino shear stress, so that's the solid line, and what happens if you, anisotropic stress, shear stress, same thing, okay? Or what happens if I just take that shear stress away, okay? And what you see immediately is that the power is enhanced once you remove the shear stress from the neutrino fluid. Okay? You have more power from multiplo of about 200 onwards. There's some mild degeneracy between this and the primordial fluctuation amplitude and spectral tilt, very mild. But what is clear is that, okay, actually there was another group that looked into this, Melchiori and Trotta, also in the same year. But they actually did a fit, and what they found, even with WMAP first year data back in 2005, they were able to exclude zero neutrino anisotropic stress at larger than 2 sigma. These days, the analysis is done a little bit differently, and I haven't been able to find another statement on just what is the exclusion significance if you just remove all the anisotropic stress. But as I said, even 20 years ago, this scenario of no neutrino shear stress was not favored whatsoever. Okay, then the question is, that's good. Can we do something with this? Well, it turns out, yes, we can. We can do a lot with it. And that is because if I go back to this picture here of free streaming and how anisotropic stress is induced, it's immediately clear that it is possible to get rid of this anisotropic stress if I make the neutrinos interact, okay? So consider this picture here on the right. What I'm trying to illustrate here is, two neutrinos that are coming head-on together, they scatter, and then they change direction, okay? They can change direction in this way and that way, but they can certainly change direction at a 90-degree angle. And what it means is that if this scattering process is very fast, then it can transfer momentum from one direction to another direction very efficiently. And if it's happening so fast, then essentially you'll have an isotropic distribution, okay? So you bring this initially anisotropic momentum, momentum anisotropy to something that has no momentum anisotropy simply by scattering. Okay, cool. So what it means is that I can use this fact, the fact that we do have neutrino anisotropic stress, that we have seen it in the CMB data, to constrain any kind of interaction process that will allow momentum to be transferred from one direction to another around CMB times. Okay, and use that to constrain any interaction strength, any interaction parameters that are associated with these non-standard interactions. So there are two things I would focus on, that of neutrino self-interaction and relativistic neutrino decay. There are other kinds of neutrino interaction that can also wipe anisotropic stress, for example, neutrino dark matter interactions. But I'm not doing that here because in this scenario, you're also involving the dark matter, so the phenomenology is a little bit different. Okay, but so we'll just focus on things that are just isolated in the neutrino sector only. So what do we need to do to constrain these non-standard interactions? Well, the most important thing in this game is to figure out what is the isotropization time scale. In other words, I want to know how long it takes for me to get from this state of affairs to this isotropic distribution. That's the isotropization time scale, given some interaction. To do that, let's go back to how we track neutrino perturbations. So I already mentioned this today in the first lecture. And essentially what we do is that we track the neutrino phase space distribution F. And to do that, we split F into a homogeneous part and an inhomogeneous part. We linearize the equations because we do linear perturbation theory. We also go to Fourier space. And then we do this Legendre decomposition. And that results in Legendre moments. L equals 0 corresponds to density and pressure perturbations. L equals 1 is velocity perturbations. L equals 2 are the anisotropies. Okay, now that's the standard scenario. If I now want to add a short-range particle interaction, then all I have to do is to add a collision integral to the right-hand side to describe the scattering processes. And then so I have that. Then what I have to do, therefore, afterwards is just to go through this process again, except that instead of just dealing with the left-hand side of the equation, I also need to do all of this splitting, linearizing, and decomposing to the collision integral. Okay, it's a very tedious process because that's what the collision integral looks like. So it can be done, but it is, as I said, quite tedious. 10 pages of calculations, and then you get the equations out. But still, it's advisable to do these calculations properly. Otherwise, you can get things very wrong. But nonetheless, it's possible to more or less understand what's happening without doing the full calculations. So let's see the next slide. Okay, so let's think about isotropization from neutrino self-interaction. So what we're doing here is that we're looking at 2-to-2 scattering. So you have two neutrinos that are maybe coming together like that, and then they scatter off each other. So here's a picture, two neutrinos, and then scattering. The point here is that the probability of the final state neutrinos being emitted in any angle between 0 and pi is the same. Okay? Head on, they can go this way or that way or wherever. Okay? So what this means is that if you now have two beams of neutrinos and they're going head on, they only need to scatter once for the momenta to be transferred equally in all directions. Only one meet will do. Okay? If you have tons of neutrinos, they only have to meet once, and then you will have a nice and isotropic distribution after one scattering. Okay? So you can bring it to that state in just one scattering. So in other words, the isotropization timescale is just equal to 1 divided by the scattering rate. Okay? So the isotropization timescale is the same as the scattering timescale. And if I now demand that this isotropization timescale be larger than the CMB timescale, then I can immediately put an upper limit on the scattering rate. Good. I mentioned this self-interaction because there's been a fair bit of interest in using neutrino self-interaction to alleviate the so-called X0 tension. I guess everyone's heard about the X0 tension. It's basically a tension between the inferred value of the Hubble expansion rate from the CMB compared with what people measure locally in surface calibrated supernova 1A, etc. Okay? And these numbers are at odds with each other by several sigmas. So that's the famous Hubble tension. And the claim of these people is that you can use self-interaction, particularly if the self-interaction is very large, like 10 to the 10 times the Fermi constant large, then the claim is that you can alleviate this tension. I'm mentioning it because it's famous. I'm not necessarily endorsing this result, but that's, you can ask me about it later if you like. Okay, so that's self-interaction. What about invisible decay? Because that's the second scenario I wanted to talk about. So first of all, invisible in the cosmological context means no photon. Okay, I know neutrino physicists think about invisible neutrino decay in a different way, but in the cosmological context, when we say invisible, it just means it doesn't, the final state doesn't contain a photon. Okay, so maybe a better word is non-radiative, but anyway. Now, so can we have invisible decay in cosmology? Well, yeah, in the standard model, it's possible. You can have one neutrino decaying into 3 neutrinos, but this rate is proportional to mass 6, so we can forget it essentially because the lifetime would be 10 orders of magnitude longer than the lifetime of the universe, so there's nothing very interesting at all for cosmology. So when we talk about invisible neutrino decay here, we are generally considering a BSM kind of scenario. So here is one where you just have very simply some heavier neutrino, still light, but heavier, decaying into something that is even lighter, and some massless boson. You can have anything you like, okay? Vector, scalar, pseudo-scalar, vector, whatever. You have more freedom to play with a coupling strength in this case, and hence the lifetime, and it is in any case predicted by, well, various models that people have cooked up. Okay? Some of which are linked to neutrino mass generation or dark matter, but that's not my department. Okay. Right, okay. So then our question here is, how long does it take for this decay process and its inverse process to wipe out momentum and isotropies? And I can tell you now, it's not the decay lifetime, okay? And that is because in a relativistic decay, if your decaying particle is relativistic and traveling very fast, then the decay products are beamed. Okay, so if you have a neutrino that is flying and then it wants to decay into phi and the lighter neutrino, those decay products will come out in a very, very narrow angle. Okay, you can estimate how large these angles are roughly. So this one here will come out, the phi here will come out at an angle that is essentially the inverse Lorentz vector, and this one here, the lighter neutrino, would be coming out at an even smaller angle because it's further suppressed by the mass difference between the heavier and the lighter neutrino mass. Okay, so highly beamed. The inverse decay is also very restricted because if you want the light neutrino and the phi to meet and then turn into coalesce and then turn into a heavier neutrino, they have to meet with exactly the right kind of momentum, with exactly the right angle before this process will happen. So what this means is that if you're trying to rely on relativistic decay and inverse decay to bring you from an anisotropic state of affairs to a completely isotropic neutrino distribution, it's going to take a very, very long time compared with the lifetime of the new age, of the heavier neutrino. But as said, you know, it looks like a horrible thing to calculate, but it is calculable, and all you have to do is to follow that recipe of you know, linearizing, decomposing of the collision integral. And the end, this is what actually we did that a few years ago, and we got this rather ugly expression which contains the boosted decay rate, some phase space factors, etc. This is not not very illustrating. I'll rewrite it in a simpler form. Looks like this. Okay, so this is basically the perturbations in the L equals 2 moment, so that's the anisotropic stress. And this is the rate at which the anisotropic stress is wiped. Okay, and that's the isotropization time scale, and it goes roughly like the 2 emission angles raised to the -2. So these 2 emission angles, very small, raised to the -2, so this becomes a very large number. You have the boost, essentially, that's the rest frame lifetime and the gamma factor of the heavier neutrino. Okay, it's model independent. You can apply this to any interaction structure that you like because all the interaction structures are contained in the lifetime anyway. The rest is just kinematics. Now, this is an interesting result because we are not the first people to think about doing isotropization from decay. In fact, the first papers that consider this problem already came out more than 20 years ago by these 2 groups. They didn't actually do the calculation, they were just guessing what the isotropization rate should be. And the isotropization rate they were using only contains 1 power of the angles, the emission angles. Okay, whereas our new result, which comes from a first principle calculation, actually has -2 instead. And this matters a lot because it's like, you know, orders of magnitude difference, okay? And so in the next slide, I'll show you some of the bounds that we have obtained. So what we're doing here is to consider just a normal hierarchy, and then you have the inverted hierarchy, and then we looked at all the possible decay and pairs that you can have. So for example, one scenario is nu3 going to nu2, and then we leave nu1 free streaming, and we just basically cycle through all possible combinations that we could have. And here, this picture here shows essentially what happens if you put in decay and inverse decay and how that changes the CMB. Probably not very meaningful, but here are the bounds. Okay, so the rest frame lifetime bound that we have is this one. Okay, if it doesn't mean anything to you, just look at this. This is our bound. The prefactor is 1.2 times 10 to the 6. This is the old constraint using the wrong isotropization time scale. The prefactor is 10 to the 9. The scaling with the heavier neutrino mass is different. We have power 5. This is power 3. And the numbers here actually come out to be, well, the 400 to 500 second for this kind of scenario. And if you have nu3 decaying into things, then the lifetime bound comes out to be about 10 to the 5 second. Just to put these numbers next to other constraints that we can derive from other probes, constraints that we can derive from other probes. So this picture here shows essentially this scenario where we have nu2 going to nu1. This is inverted mass ordering. and the bound is here, the orange line, and everything that is below is everything that's below is allowed, and everything that's above is constrained. Okay, and what you see here immediately is that this CMB limit is pretty good. It's better than the ice cube constraint at the moment, better than supernova 187A, and you can also get bounds from BBNs or neutrinos and laboratory experiments, and these are relative to these other bounds here are, well, they're not even featuring on the plot. They're not terribly competitive. But the coolest thing here, I think, is that if you look at the forecast for what ice cube and future neutrino telescopes will be able to do when it comes to pinning down the constraint of neutrino lifetime, these forecasted constraints are actually lying very close, and in some cases even above the current CMB limit. So that is actually very nice, because now there's another probe that is probing the same region. So I think that's very cool. This is kind of similar, but for a different arrangement, normal ordering. You can see a very similar story again. So that's the cosmological bound, and then you have the forecasted sensitivity for ice cube and other neutrino telescopes. So, and I think I am done, and I'm right on time. And so here's my summary, and thank you very much for coming to these 3 lectures. Yeah. Yes. Yeah, it is. Yeah, so the main thing here with this picture is that, which picture is that? This picture. This picture is that the phi particle that is produced is taken out of the energy density of the neutrinos themselves, because all of this takes place after decoupling. Okay, so you're just passing energy between neutrinos and phi back to neutrinos and so on and so forth. So you're not changing the energy density. There's no any effective constraint or whatever, because you're not producing any energy. Producing new energy densities. Yeah.
So the n-body simulations that you do, does they depend on the initial conditions?
Very much so, yes. Yeah.
One more question I have. So you were showing some slide where they considered different statistics. Now, how can neutrinos violate the Fermi-Dirac statistics?
You could imagine a case where you have, let's say the neutrinos are decoupled already, and then there's a decay process that dumps some extra neutrinos into the mix. Then you could, for example, have a bomb somewhere. That's how you can get away from Fermi-Dirac distribution. Or you can have the decay happening while the neutrinos are still kind of coupled, but you don't have enough time to for the weak interaction to kick the distribution back into a perfect Fermi-Dirac form. Then in that case, you can again have some kind of distortion. It's out of equilibrium. Yeah, it has to be things. I mean, the weak interaction process has to be not operating the most efficiently for these distortions to survive.
If there are no other questions, I don't see any hand.